Hi everyone, my name is Qua Nguyen. I'm working with Professor Tae Kim. So today I will talk about joint hybrid delay and phase recording under true time delay constraint in a wideband massive MIMO system. So here the outline of my talk. So first I will go for an overview about the terror communication. Then we will talk about the beam screen effect, which is a critical issue in terror communication. Then in the problem formulation section, I will talk about how do we deal with the beam screen effect. Then we will verify our proposed method in the simulation section. And at the end, I will draw some conclusion. So let's start with terror communication. So we know one approach to increase the wireless system capacity is to increase the bandwidth. So based on this observation, the terror communication has attracted significant interest from both academic and in the industry because it can offer ultra large bandwidth, let's say tens of gigahertz bandwidth. So for example, the 10 to 100 gigabit per second data rate can be achievable. Then that's why the wideband communication is a potential technology for the future wireless communication system. So, but the communication in teraband faces a challenge that's in a very high loss. For example, at 160 gigahertz frequency, we will face around 80 dB per kilometer cut loss. Then to deal with this high cut loss, people use massive MIMO technology to generate the directional narrow beam to focus the energy of the signal to a specific direction. So we can see here the difference between the massive MIMO system and the legacy antenna system. The massive MIMO can focus the energy of the signal to a specific user. So that's why it can overcome the high band loss in a high frequency. Then in order to do that, we use the hybrid precoding architecture for massive MIMO, which include a digital precoder and an analog precoder. So digital precoder will do digital signal processing that like power allocation, and the analog precoder will do the beam forming. So the popular hybrid architecture is the phase shifter based hybrid recording, which include IF chains and phase shifter. And the role of the phase shifter is to create frequency independent phase rotation beamforming matrix, which help to point the signal to a specific user. Then it is shown that this hybrid architecture can approach the achievable rate performance of the fully digital precoding architecture. But the underlying assumption here is that we are considering the narrowband system. Then when we move to the wideband system in teraband communication, the question is, can we get the same performance? Then is it challenging due to the beam screen effect? So the beam screen effect, basically the beam screen effect means the beam at different subcarrier point to different direction. So you can see here the difference between the narrowband system and the wideband system. So in the left-hand side figure, you can see the beam at every subcarrier, F1, F2 to the Fk, they point to the same direction. But in the wideband system, the beam at F1 and F2 to the Fk, they point to different direction. So what is the consequence of this effect? Then it will cause substantial array gain loss at different subcarrier frequency. And we can look at this example to visualize this array gain loss. So let's say we have a system with a carrier frequency 300 gigahertz, and the bandwidth is 30 gigahertz, and we have 129 subcarrier frequency, and we want to steer the beam to the spatial direction 0.5, which corresponds to the 30-degree angle departure. And we are assuming the uniform linear array with 128 transmitter antenna. So you can see here the beam at the first and the last sub-area, they are squeezed to different direction. Then only the central sub-area frequency can achieve 100% array gain, and at the 0.5 spatial direction, but the first and the last sub-area, they can only achieve 20% array gain at the 0.5 spatial direction. And it wasn't when the number of transmit antenna grow. So, and you can see in the right-hand side figure, when the number of transmit antenna grow, most of the non-central sub-area frequency, they suffer from 100% array gain loss, and which is quite contradictory with the benefit of increasing number of transmit antenna in the wireless communication system. So the question now is, how do we ultimately compensate for the beam stream? The traditional approach in a millimeter wave system is the beam broadening technique. So the idea is we want to generate the wider beam with large beam width so that they can cover the screen direction. And this method shows the effectiveness in the millimeter wave system, but is ineffective in terrestrial band because in a terrestrial band, some of the beam will be completely split from the spatial direction that we want to transmit the signal. And now there are people interested in the two-time delay precoding architecture. So the idea of the two-time delay precoding is we want to generate the frequency-dependent beamforming matrix. And we know the delay in the time domain is equivalent to the frequency-dependent phase rotation. And this architecture really improved the array gain performance, which means it can compensate for beam stream, but it requires more hardware device and more power consumption. So here's the two typical two-time delay hybrid massive MIMO and phase interface hybrid massive MIMO architecture. So the difference is in the two-time delay-based hybrid massive MIMO, we have a layer of two-time delay device in the analog recorder domain. So we want to, in general, we want to design the analog recorder, which include two-time delay and phase shifter to compensate for beam spin effect. So in the prior approach, people fix the phase shifter value, and they only design two-time delay values. And they also assume that the two-time delay device can generate unlimited two-time delay value. But in practice, two-time delay range is usually restricted, for example, from 0 to 500 picosecond. So this observation really motivated us to jointly optimize both two-time delay and phase shifter value under the practical two-time delay constraint. So now we go to our problem formulation. So let's say we have this two-time delay based hybrid decoding architecture as in the right side figure. So the received signal model can be modeled as in this equation in the left-hand side, which is a YK, and it equal to the product of the channel matrix and the analog recorder, which includes two-time delay and phase shifter recorder, and the digital recorder, and the transmit symbol, and the noise NK. So our goal is to jointly design F1 and F2K, which is the phase shifter and time delay matrix to maximize the array gain under the limited two-time delay value constraint. So the design method is distance minimization. So here's our problem, optimization problem formulation. So what we did is we optimize the distance between the optimal analog encoder that can completely compensate for the beam stream and the product of the phase shifter and true time delay matrix. Here we have the practical true time delay constraint. That means the time delay value are restricted from 0 to a P-max value. And we have a set of analog recorder constraint. So usually directly solve this problem is challenging because we can see in the objective function F1 and F2 they are correlated, and we have a bunch of non-convex constraints. The popular method to deal with this type of problem is we want to find a suboptimal solution by relaxing the constraint and using the power coordination descent algorithm. But our idea is different. We transform the problem into the place domain. Here's the idea. Let's say we have 2 points A and B in the unit modulus circle. Then we see that minimizing the distance between A and B equivalent to minimize the place difference. So based on that, we can transform our problem from the unit modular domain to the place domain. Then we have theorem that the transform problem is linearly constrained quadratic programming problem. So we can characterize the closed form optimal solution. So you may want to ask what the benefit of using this complicated computation method. So the first benefit is we can have the hardware selection criteria. Let's say we have n TCD per IF chain and TMAS. And in order to effectively compensate for the beam stream, the TMAS should satisfy this lower bound, which depends on the number of transmit antenna, area of frequency, and the number of TCD per IF chains. And another example, if we have M star, the minimum number of required TCD per IF chains, we generate the aggregate threshold Z0. Then M star can be approximated like in this equation. That means M star increases linearly with respect to the bandwidth B. So for the simulation, I will go very fast because of the time limitation. So here, first we evaluate the aggregate while we increase the number of transmit antenna. First, then we see our approach outperform the benchmark. Let's say 80% of our Webber superior have the aggregate greater than 0.9, but in the benchmark, there's no Webber superior can reach the same performance. But we see the similar change in the aggregate performance when we change the DMAS and pick the number of transmit antennas. And the similar change in the attribute rate performance can be observed as in this slide. However, this scheme has some limitation. It requires perfect channel state information, and we assume the high resolution two-time delay and phase shift value, and it's not optimal attribute rate design. But for the ongoing research, we may want to take into account the near field effect, and we want to explore the beam speed effect for reducing the overhead of channel tracking or user localization. So, for conclusion, because here I want to say that we propose a hybrid recording approach for compensate to effectively compensate for beam speed, and we characterize the optimal solution of the delay phase shifter. Then I think leveraging the beam speed effect is a promising direction for the future research. That's it. Thank you for listening. So I'm happy to have any questions.
Thank you. Any questions from audience?